rising EV adoption, which is driven by environmental concerns and technological advancements, which is the energy efficient. The another one is the two-wheeler EVs are especially popular in urban areas, and that's why the onboard chargers are come into picture to design the charger compactly, efficiently, and the charger should grid compliant. Then the software I use, the MATLAB simulation, enables the performance testing and the optimization for the simulation studies. This is the problem statement of my project, that the existing onboard chargers of electric two-wheelers are inefficient, bulky, and fail to meet the power quality standards. Then I have tried to design compact, high-efficient solution for that, which ensures the reliability and the compliant charging. The objective of my project is to monitor the real-time factors for the efficient onboard charger using the MATLAB. The another one is to integrate the topology which I used, that is totem pole PFC plus full DC-DC converter. For this topology, the switches I used that SIC MOSFETs to reduce the switching losses, and the next one is to simulate that simulation and analyze all the system performance. Firstly, I have studied the several traditional converter topologies. First one is a boost PFC converter, then VNR rectifier, then the totem pole converter, flyback converter, and bidirectional converter. As we know, the boost PFC converter is used widely, and it is very popular in the EV chargers. Another one is the VNR rectifier. It is a three-level converter, which is used for the high power applications in the charger. Another one is a totem pole converter, which I have used. It is generally used for the low to medium level power applications. Another one is a flyback converter. It is basically used for the galvanic insulation and for the protection purpose. Then the last one is the bidirectional DC-DC converter. It is used for the bidirectional charging connectivity. Then this is the comparison of all the converter topologies. The first one is a boost PFC. It is used for the single phase boost. It is a single phase boost converter which is used for the two-wheeler medium level or low level EV chargers. The switching devices generally used for this are the MOSFET and diodes. It shows the high efficiency from 90% to 95%. It does not have any bidirectional support. It has medium level power density, and the application of the boost PFC converter is it is a AC input PFC for front end converter. Next is the VNR converter. It is a three-level rectifier. The switching devices are used in that converter are the 3 MOSFETs and 6 diodes. It has a very high efficiency, which is 95 to 97%. It does not have any bidirectional support. The power density is high in that converter. It is basically used for the 3-phase onboard chargers front end. The next is the totem pole PFC. It is used for the single phase EV chargers. It is a bridgeless PFC converter. The general switching devices used for that are silicon carbide MOSFETs. It has very high efficiency among all these converters, which is basically 96 to 98%. It does not have any bidirectional support. It has very high power density, and it is very compact device. It is very compact converter, which gives the high efficiency for onboard chargers. The next one is the flyback converter. It is basically used for the isolation devices in that are used are the MOSFET, which is the most fast switching devices. The efficiency of this is a little bit lower, which is 85 to 90%. It does not have any bidirectional support. It has low to medium power density, and it is used for the low power isolated chargers. The last one is the bidirectional DC-DC converter topology. It is basically buck boost or dual active bridge topology. The switching devices in this used are the silicon carbide or gallium nitride MOSFETs or IGBTs. It has very high efficiency, varies from the 92 to 97%, depends upon the application which it is used in that. It has the bidirectional support. It is generally used to the V2G or battery to grid like applications. It has very high power density, varies from medium to high level. The conclusion of this converter topology, comparison of this topology is the total PFC topology is the better than all the converter topologies for the application that I have taken this EV charger.
So you would have mentioned like from where you have taken that table, some reference contained or reference name would have given here. It's taken from some reference name.
Yes, this is from the
must highlight that from which reference you have taken this comparison.
Application, have you mentioned anything about application? What application are you considering?
It is a EV two-wheeler.
Reflecting in your title, or it's not reflecting in your title?
Yes, it is reflecting. Before the simulation of total pole converter, which I used, I simulated the boost and flyback converter topologies for that charger. This is the graph which shows the flyback converter output voltage. We can see the it is showing too much fluctuations and ripples in the output voltage of this. And another graph is the harmonic spectrum. We can see the surges and the noise that we are. We can see that in the flyback converter. This is because of the storing elements and all used in the flyback converter. So this converter and this is the graph of current harmonics of the flyback converter. So it is showing the too much fluctuations and ripples in this graph, and we can see that the effective spectrum of the output current. So by this simulation, we can say that this is not the compatible converter topology for this charger. Next, I have used the boost converter. Boost is a very popular converter topology in the EVs, but still it is showing the little bit noise and switching losses. It showing that the switching surges, and it does not meet that level of the current values and voltage values, and we can see the distortion in the waveforms of this. So I have moved forward to the totem pole converter. This is the basic circuit of the totem pole converter charger, which includes the totem pole converter and the isolated full bridge converter. This includes the switching devices like silicon carbide MOSFETs and the isolated full bridge converter and the totem pole converter connects to the DC link. When the AC supply is given to the totem pole converter, it boosts that voltage to the 400 volt. It is basically boost converter derived topology. So then inductor helps to boost that voltage, and then this voltage is again transferred to the isolated full bridge converter as the input. Then the isolated full bridge converter converts this to the AC, and we can see the transformer for this isolation. It converts the high level AC to low level AC voltages, and the diodes, we can see diode bridges that converts it to the 16.67. It is the required current and voltage rating for our application. It is the SimScape circuit of the charger, which we can see the MATLAB SimScape simulation which I have designed. It includes the current sensor, voltage sensor for the measuring and all the cases. Then at center we can see the converter, which is the potential converter. After that, the filter capacitor we can see. Then this is the basic circuit of the total pole converter. It is the converter which performs its application based on based on the scenario that it has two legs. The first leg is operates at the high switching frequency, and the another leg operates at the low frequency leg. The high frequency is basically switching frequency. It varies between the 65 kilohertz to 100 kilohertz, and the low frequency leg is the power frequency, which is 50 hertz.